So this video is literally on the graph. I'm trying to formalize it now. So you have the let me formalize it now. So you have define a graph G equals to U, V and W. This is not recording my voice. This is recording my voice. So define a graph. So define a graph G equals to U, V, and W, where U is the user, V is the institution, and W is the arbitrary third party. This is one of the three-player chess of the system, because this can be a good person or a bad person. A malicious actor. Now, T is equal to the change in D, uh, which is given as the magnitude of D squared minus 4AC. Which is basically double magnitude, which is basically t. Where t is the time, changing d is the change in the spooling, uh, uh, b squared minus 4ac. B squared minus 4ac refers to the quadratic equation, uh, b squared minus 4ac. Um, so we're gonna have the quadratic equation, time of the system, equation. We're gonna have a model graph. So this model ensures that you have living breathing entities of the graph that actively being like a star. But the A star algorithm has a start, a goal, and the history function functor. Uh, H. Uh, mm, so uh, so Dijkstra explores all direction. A star explores the heuristic function. Uh, that's interesting. So I think I'll use Dijkstra algorithm to do this. Uh, for closer centrality. But any heuristic function would be another better doing it. So this is the directional representation of the suing system. So you go to this to sue someone via the firmware, and the firmware would uh, pop up on your screen. You can always log into your firmware, but the firmware is basically the firmware or the microbit system that is to sue someone whilst you're just sleeping. But you can take this via symbolic interpreter or probe and do this yourself. Listen, so the system does this. So you have a qubit. Now, a qubit is basically uh, a system of, the qubit is basically the first qubit, the color qubit, but it has a fingerprint. So you have an AST, and AST is equal to fingerprint, but that fingerprint is the artifacts of the NSIGII file firmware. For example, you can have a hexagram of the artifacts you have via the boot sector. So the boot sector is defined again as basically when you load something, you're loading the artifacts uh, L0. You can't find that video anymore. Uh, but it has to be cross put. So let me just continue doing it. So what am I trying to prove here? I'm trying to prove uh, that you find a graph G equals UVW, where you use the user, V is the institution, and W is the arbitrary third party, or the malicious actor, the person that wants to get something from the system. I'm trying to ensure the FN equals to GM, no history explosive direction. Split resolution is basically uh, the, the foundation of the digital system. So you're gonna have a queue. Um, so let's go this algorithm. Let's do the math first. This is the math I'm doing first, then we'll do the algorithm. So let q uh, equal to b a q q. Now the q create a q that maps tripolar state of the discriminants. Uh, okay, let's q be a set. Let's q and s be a set. So s is a set of let s let s colon equals to a a set that contains uh, all the elements of the map. So you can have a mapping. The, so you can have the irregular mapping. So you're gonna have you be the oh no, this is a frequent. So let's a map m equals a map um let's a map of three colorable graph three colorable graph b u u is green u is green green yellow or orange green can be green yellow or red yellow or green will be green 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 we define is okay you when you is yellow is what is a warning and you red when it's danger so this is triple colorable but triple so you're gonna have u green yep so the drift theorem is uh, uh, d is d half d v the drift of diff of uh, a graph g is equal to uh, 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 v v t minus t t no pt minus ct now pt is the time minus ct is current potential where uh, uh, p is the projected point uh, uh, c is the camel point so this is before drift is in strident ruling, which is a final decision. Uh, uh, D drift G drift of a graph uh, implies P uh, P external uh, basically a probe uh, a probe let's say a probe word probe external equals to a probe external given T a external probe T, that takes some data, implies T, implies some state, implies some data, such that, such that B, uh, B squared minus 4AC, or, or changing, or delta, uh, or delta, uh, T, uh, less than 0. Basically, if the delta T is less than 0, if T is less than 0, that means there's no solution, and two parties, uh, institutions, leaving us, are ghosting us, ghosting the process of delivering food, water, and shelter. So basically, when T is less than 0, uh, if T is equal to 0, there's an equilibrium uh, uh, in the system, and one solution entangled via a qubit signature. So the qubit signature again works kind of the probe AST. So what I'm saying in this solution is there's three states to the system. Green. If it's green, the system. If the user is green, then it's okay. If the user is if a graph is green, yellow, red, that means the green is okay. Yellow means it's a warning, and red means a danger. You know, but where so, so basically, the drift is geometric, and works in kind of principles of spring physics. But that's what I'm saying. The spatial inclusion was literally to measure delay, denial, and the fair. So this probe is called. Uh, so a probe can be it's part of the history. So you have two types of probes. You have the method probe, usually the delay, deny, the fair, or the fan. Or you have a reticle, reasoning, rational probes. So the probe doesn't answer solve questions. They work on dual interpretation of system, and they are symbolic by nature, by design, because they allow you to evaluate proven state. So basically, if you have the A-star algorithm, the A-star algorithm will be expressing such systems, uh, but probes are A-star bound. This is directional prediction for closeness. So this will, if you want to include this stuff included into the system, so you're gonna have uh, Dijkstra, which is Fn equals Gn, where Gn is the graph isomorphism and N is the input of the nodes, uh, N is the nodes, you know, but A star has Gn uh, uh, plus Hn, where N is neutral. So this is what we're going to do the rationale. So, the P2 system is a linear source upward isomorphism. everything is algorithm, but I'm only implementing the show for now. So you get a drift theorem. The system's leaving us. They're leaving us. Uh, they're liable to a lawsuit. System has a symbolic interpreter state. The interpreters basically collect the receipt in three ways. They collect it in here and now. Here and now, they've left off. So here plus now, there plus then, and when plus when. So this model of delay, deny, defer is equal to the probe state via cybernetic principles of human suffering. Uh, you know, so the probes are very important to understand because they'll lead us guesswork, but they operate on principles of computation. But my probe is basically model based on telemetry because if he knows enough information, it doesn't need to guess anything. If he has enough information, he gets this cybernetic device. So what am I really saying here? So a drift is the trident rule. So drift of a graph equals to p, the precision point, over time, where time is the change in d, and the double magnitude of b squared minus 4ac minus ct, which is equal to g. That's the definition. Let me show you my work, guys. So right down. It's there, it's there, and it's there. So you can see the drift. Sorry, the drift of the algorithm is there, and the algorithm is a drift function. Uh, yeah, the system also going to so how does the drift work? So the drift has got two algorithms. So it's tripartite. So it sues you as you to leave. You have to calculate the money, but it has to basically companies owns this, but you firm encode software by recording the system. So you can export the document uh, and upload to the internet. So or go to a lawsuit. But this is a firmware basis. It's gonna give you food and shelter. But security, uh, but whatever application was installed. Now, the application part is the AST part. So the AST part is like you have a program, you get an AST signature, an application system signature. Using kind of some Python. You know, you don't import it. You don't. You just get an application history, and they align and stuff with the qubits. So let me write them draw it here. So let me do something. I want you to remember. This is in the people. I guess it's up and running now. Oh, oh, shit. We're gonna have uh, high 4.3 high. I have a physical cube. Doing it here. So basically, you have a surface, and that surface is a cubit, which is a cube. It's a face of a cube. So you have a face of a cube here, and that face of a cube contains some signatures. So every component is verifiable with an MD5 file. So they lie on the grid of a system with MD5, the MD5, MD5, MD5. You can have the checksum like A012, like 512 block digest of the facts of the file as a type, yeah, the fact format, the fact, the 512 blocks, and that 512 byte of boot sector lies on a probe lattice. So the probe lattice will be have so this is basically a cube face, basically the front of a cube face. And this is a cube face, but a qubit face. So it's just a qubit face, and this qubit face is just one face. How many sets of cube? You have six faces. You're gonna have the front face, which gives you the front component of the system. Uh, but you're gonna have one component, but it's like this is just like one component based on a qubit model. So you're gonna have this component, which you can even see, and she's gonna have phase one. Basically, you're gonna have the fingerprint. Now, fingerprints are just MD5 hashes, but the sum of the two fingerprints is basically timestamped, hashed, timestamp, hashed, MD5 or SHA-256, hashed, uh, forwarded. No, like my video based on the geometry of some. This is the front face, front face. So you're gonna have a front face of the system there, and that's one cube there. One cube front face there. You're gonna have uh, uh, still respect that kind of topology setting. But that's what I'm saying. The NSIGII model still applies. So you get Alexa, a parser, and an AST. Now the AST finger is going to hex dump. So you can have a hexagonal dump of the AST finger, and they match the signature of the MD5 signature. So you have like 12 MD5 section. You can have like let's say you have every loaded component. There are 30 loaded components of MD5, 30 MD5. Let's just say there's 15 MD5 or 15 MD5 components that are loaded in by the NSIGII firmware. And those firmwares are literally have an AST. Now, the program takes the AST, and that AST gets a hex dump. So the previous hex is a mode down. And that's basically which can be read in boot sector via a timestamp. So you have a boot sector as a timestamp, an MD5 fingerprint, and the signature. The signature of the total MD5 system verifies that component via a single verifier, and that is what allows you to sue people. Because you can take this component, uh, you know, you know, if it's MD5, the signature is MD5, can undo this MD5. We take it up because MD5 is already broken anyway. You can get your suit. You also sort it out into the key face. So the keyboard has faces, and the faces are because it's a topology computer system. It was kind of spins and ups and downs, spin up, spin down. No, but it's going to give you a clear picture on the words there, so you can get some money in your bank account. So it soon counts as for money. Stay to go there. Uh, so you have a map of Python column. So the system has basically has a job. So the two you can have you can have three d sub one. Uh, so you can have d prime, d prime, d prime, uh, the, the prime of d. So uh, uh, let's call it du. Uh, so you can have d. So you can have d prime u of u of U given V, which is basically the change drift um, given T, D prime. So that's the roof prime. So this is basically D prime represents uh, the derivative of U given V, OG, 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 OW, U, over W. Now, if you obviously, this is probabilistic because if you are the user and basically this is Bayes theorem, uh, Bayes theorem, uh, in probability, which basically means you have a three-way Colourable system uh, via the swing process. So let me just try and find that really. Uh, Bayes, Bayes theorem, Bayes theorem, Bayes, Bayes theorem. So you're gonna have probability of A given B uh, is d prime of u. Uh, so basically, you're gonna have du. Uh, so determine the money of some sum. The probability of A, let's see, then A also called B. So this matter is because of drift. So you're gonna have d prime u uh, given v uh, b uh, equal to the probability of d uh, uh, probability of d. Basically, let me try and run another sense. So you have probability of d, uh, probability of, probability of d. Because this run the system down, but I'm trying to run it. So you have 2/3. Uh, One, so basically, you should have the weighted average of 2 points, but you're gonna have them graphically as probability theorem, Bayes theorem. So, I'm trying to write it down properly. So d given d of the d prime of u is given v, where v is institution that's ghosting you, and w is the arbitrary third party, implies that probability that the probability of you are moving away from the system. So you have three types of drift. You can have uh, uh let me start again. So you have three types. You have drift away, a bypass to drift away towards uh, towards wait, you have drift away. So you have drift towards drift away, which is basically opposites opposites of drift away. Uh, drift uh, drift towards uh, the drift orthogonal drift orthogonal orthogonal. So you're gonna have just I don't know how to measure events or probabilities to it, but I don't use this formula. So you're gonna have the proof of Bayes theorem. This is Bayesian networks. Yeah, so these are called Bayesian networks. These are probabilistic graphs. So it's not just machine learning. It's gonna estimate the system of the prior and posterior. Where the prior is the initial probability of an original component before any data is taken into account. Um, and the posterior, which is the other probability of information. But the probability of a contribution given A, this is a PA given A probability. But this is a Bayesian theorem application. So it works in kind of probability graph. Definitely want to use spring theory because the spring theory So if you put the half of the force, usually base theory and string theory, and spring the spring. So drift. So let me try and do it away. So drift tools, drift tools away, the drift tools away, and the angle, orthogonal angle, will have. So drift towards will be drift away. Drift, let me say, drift. If it's just ghosting you and it's drifting away from you, you have a way. So drift away, define. Drift away is giving you, you, uh, you given v w uh, equals the probability of, of du given du given v or w. The drift away will give you the that the probability the probability of away the way away will give you the probability of um the posterior of events happening, which is 1 minus t times c times p, which is that 1 minus t times c plus t times p, where t and p is supposed to be, you're gonna have 2/3 uh, 2/3 t plus 1/3 p, which is the the uh, algebraic form of p over the weighted average. Now, that's what I'm saying. This is basically the once you calculate the Hamilton system. So drift away will become given u u given u given uh, 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 so the drift away. So basically, drift away basically is spring of one half. So you're gonna have away. So if they're leaving you, the probability they'll have to be who's got numbers there. I can't remember the numbers. But the initial condition probability is random values. I'm just trying to find this model. So let me just write down drift away. So drift away is given as so let me just write away you given v, so which means to be two equations two, which means this expounds to d drifts up away will equal to uh, uh, uh db d d d drift away view. Because if I'm just doing one, the maximum will be the v decision leaf as well, and that'll be away. So that'll be v v b given a given b. So b will be a. So b given a when a b will occur. Probability of a when you so b there'll be b given a into b. So you have two equations. You're gonna have the drift probability of a drift probability of a. So you're gonna have two. We're gonna have drift way equals to uh, the moving away, diagonal moving away, right angle and moving away based on the b squared minus 4ac. When oh yes, the way when b when b squared equals to 0 equals to more than equal to b when given that given given uh, b uh, b squared b squared b squared minus, given the magnitude given c uh, b squared minus 4ac minus 4ac equals it's less than 0. It's less than 0. Let's see, it's equal to 0, less than 0, and that will be uh, less than 0, uh, less than basically you can have two solutions. So if it's away and it's a diagonal, that's basically yellow orange. So you can have the color yellow, the because moving away, this is just yellow, orange. This is a bipartite color. So basically, the three colors, yellow and orange, will be here. This is the color between yellow and orange, which it's moving away from you. And they're gonna have b squared minus 4 is less than or equal to 0. And then now b, the way will be uh, u, the probability, g squared, you might say what type. The away, where the square root of b squared minus 4 is equals less than equal to 0, and t and t uh, basically the magnitude of b squared basically you can have two sources. So what does b? Let me just try to write on the page. So I'm feeling this. The one thing is that this is gonna get kind of too long. It's not really working out for me. I'm four lines in, but if you're drifting away, the goal is if you're drifting away, you have two states you're in, which is b squared minus 4ac, uh, which is basically the change in d. First one, G1, D1, which is the first derivative of D, which is the uh, the uh, the magnitude of which is basically uh, the the Manhattan distance, uh, the Levin distance of the G. So you're gonna have the how many distance would be Manhattan distance would be square root of x squared squared plus y squared. So how many distance again is x1 x1 minus y x2 uh, plus y minus y2. That's the Manhattan distance, which is basically vertical rotation. We have the Euclidean distance, which is basically the square root of x1 minus x2 squared, not plus, uh, plus y1 minus y2 squared. So the square root of these two terms is called the Eulerian distance. So I'm trying to take the measure of the distance over the graph, cost of the graph, but the graph is not defined. So I'm going to formalize the logic so I can apply it, but it's not working out. So basically, the graph is by three-way, what I call three-way bipartite colorable. So you have the three-way graph. So you can have because there are three actors in it. They are the user, the institution V, and the arbitrary third party W. The three-way colors represent red. They have two colors, two standard colors. So can be they have bipolar color. They have two-way coloring. Uh, but they have like they go on spectrum. Uh, so you can have light green to dark green, uh, light yellow to dark yellow, uh, light red to dark red. Or uh, uh, basically, you can have basically that's a good one to have. You can have uh, the system have so for example you can have three color element based on the choice. You can have red, green, and blue. Red, green, and blue. So three colors there: red, green, and blue. Red, green, and blue is literally uh, uh, system. Uh, they have a time. So uh, the double matrix will give you the time in in a space. Uh, but you can no, that means the integration. So you can do the integration all the time in system. So the goal is to model this uh, as a three-way column block. So where did I stop? So you have for the 2 minutes left. So you have 5 more minutes. So T equals the chain in D equals B squared minus 4AC. Minus 4AC, but you have the the graph, which is basically y equals uh, basically you're gonna have the c squared equals um, s squared equals uh, 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 s squared plus y squared, basically the time capsule over an event. Basically, the time capsule is basically what the event has. Model basically what the time capsule does. So you can have r squared. R squared equal to the radius of the times t squared, or you call it time contribution, because space cancel s squared, you have time for t squared, and the space, basically, if you have 60 frames per second, you have 60 frames for every 1 second. What the domain is 60 frames, what the domain is 60 frames, and the range is 1 second, 60 frames to 1 second, but that comes down to 60,000 uh, nanoseconds to 1 second, um, uh, processed by graphics card. So, then you have a range of 60 to 60,000, 60 seconds, 0.69 seconds. Basically, I can't remember the time capsule there. How do I do the time capsule? So the time capsule will be the space is shared from the system. I was going to turn off, but the time is quadratic. Okay, you're going to process also of the three-way column. So three-way bipartite covering of each graph, U, V, and W. So you can have blue and orange or something like that, but there's two colors for every graph basically, and that's the goal. Then you can have a three-way colorable system that tells you how system drift if someone's not respecting their own policy via the probe. Now the probe is defined as delay, deny, defend, or defer. Delay means they're delaying you. Defer means they're denying you the right, and defer means they're leaving you. They're defending their business. This is what litigation does. It's a symbolic litigation system. This is my work with the all the assets are linkable, then executable. Thank you, Joe.